Hello PreCalc, here we are with 7.3 multivariable linear systems. We just finished up with substitution, elimination, and graphing. Okay, the method of elimination can be applied to a system of linear equations in more than two variables. This easily adapts to computer use for solving linear systems with dozens of variables. When elimination is used to solve a system of linear equations, the goal is to rewrite the system in a form to which back substitution can be applied. Consider the following two systems of linear equations. System of three linear equations in three variables. We got x, y, z, x, y, no z, x, y, z. And this is the exact same system of equations rearranged to be in row echelon form. What is row echelon form? It is the stair-step pattern with leading coefficients of 1. So we have 1x, and then the y, and then the z, and underneath of that 1x there's no x's. And then on this same line here, now we have 1y with whatever z's, and then underneath of it there's no more y's. And then we just have our 1z. So we're able to get all the way down to the bottom and use back substitution to climb back up the ladder. Example 1. Let's use back substitution to solve. So, ta-da, z equals 2. Well, if I know z equals 2, let's put that in there. Y plus 3 times 2 equals 5. And we'll get y equals negative 1. Well, now I know z and y. Let's put those up here. X minus 2 times negative 1 plus 3 times 2 equals 9. Okay, 2 plus 6 is 8, and x is 1. So now I know x, y, and z. So my coordinate triple is 1, comma, negative 1, comma, 2. X, Y, Z in the three-dimensional plane. Two systems of equations are equivalent if they have the same solution set. To solve a system that is not in row echelon form, we first want to convert it to one that is. What can we do to convert it to row echelon form? We have three basic row operations that we can use. We can interchange two equations, or flip-flop two different rows. Row 1 is now row 3 is now row 1. Multiply one of the equations by a non-zero constant. We've had plenty of practice with this when we did our elimination. And then add, this is a new one, add a multiple of one of the equations to another equation to replace that equation. And we'll get a look at that here shortly. Okay. Rewriting the system of linear equations in row echelon form involves a chain of equivalent systems. Each is obtained by using one of the three basic row operations. This process is called Gaussian elimination after the German mathematician Carl Friedrich Gauss. Okay, let's see. Now for our first time, we're going to do one step at a time. And after you get used to this method, you could probably do step 1 and step 2 together at the same time. There is a lot of writing, so let's make sure we are trying, I don't have very good handwriting either, but let's try to write nice so we can read our writing and don't lose any negative signs. Okay? So, remember, we want it to be stair steps with 1x, 1y, 1z. So I like that we have a 1x here already. So now I want to get rid of the x's below it. So we're going to jump right into our new one, our new row operation of adding two rows together and replacing it. So I am going to add row 1 to row 2. And we're going to use that to replace row 2. This is going to be the new row 2. Okay, so we have to rewrite this. We got x minus 2y plus 3z equals 9. And now we're adding these together, and that's going to replace row 2. So x and a negative x, no x's. Negative 2y and 3y, we got 1y. 3z and no z is a plus 3z. 9 and negative 4 is 5. And then we didn't do anything to this one, so we write that one down again. A lot of writing. Very important that it's neatly organized. Okay, so we're still not done with our first step. Again, we want 1x, and we don't want any other x's left. So now I'm going to add a multiple of this one to cancel out our 2x. So it's kind of like a little bit of elimination, I guess. We're going to go negative 2 times row 1 and add it to row 2. Or row 3, excuse me. So, top row remains unchanged. Second row, no change. And that's why, as you get going here, you'll catch on that you could have done this one and this one on the same thing. Could have saved you a step. Okay, so here we are. We're at the new one. Negative 2 times x, and add it to this one. Those are going to cancel out. Negative 2 times negative 2 is plus 4y. Add it to here, and negative 4y, we have minus y. Negative 6z plus 5z is negative 1z. Negative 18 plus 17 equals negative 1. Okay, fantastic. We've gotten 1x with no other x's below. Next on the stair step, we want to have 1y with no other y's below. Okay, well, I still have a negative y. So an easy fix here is to add this one and this one together, and that should take care of our y in this one. So we're going to go r2 plus r3. And we're going to have to wrap back around to the front over here. No change on the top. X minus 2y plus 3z equals 9. 1y plus 3z equals 5. And now we'll have, okay, those would cancel. 3z and negative z is going to be minus 2z. Nope, positive. Positive 3, negative 1. Positive 2z. And then 5 and a negative 1 is 4. Okay, we want 1z. So maybe you go, oh no, and just scribble it out and write the simplified version down here. But we're going to go the distance here on our first example with this. Okay, and now we're going to multiply row 3 by a half, multiply by a non-zero constant. So 1/2 times r3 and finally we get 1z equals 2. And now, do you recognize this? We should be back to where we were in example 1. We're back to where we were in example 1. So we're not going to solve it again. Okay, we already did that back substitution. This should be exactly the same as we had over here. And we should get 1, negative 1, 2. Okay, as with a system of linear equations in 2 variables, the solutions of a system of linear equations in more than 2 variables must fall into one of 3 categories. Linear systems, remember, linear systems. So exactly one solution, infinite solutions, no solutions. Okay? Linear systems, they're all the lines are going to cross at one point. They could all be the same line, overlapping lines, and have infinite, or there'd be no solution. No point that satisfies all the lines. Okay? We have learned that a system of two linear equations in two variables can be represented graphically as a pair of lines that are intersecting, coincident or parallel. Coincident meaning the same. Let's see what happens here with 3. Okay, so we got 3x minus 2y plus 4z equals 1. X plus y minus 2z equals 3. 2x minus 3y plus 6z equals 8. Okay. Well, our first goal is to get 1x. Okay, and I think the easiest way to do that is to swap row 2 and row 1. Okay, and now we will have x plus y minus 2z on the top equals 3. And now this is my new row 2. 3x minus 2y plus 4z equals 1. 2x minus 3y plus 6z equals 8. All right, and let's try to kill two birds with one stone here. All right, this is kind of like how I was talking about before when we have our 1x up here, and now I'm trying to get rid of the x's below it. Let's try to do two steps in one here. Okay, so to cancel out the x's here, we're going to go negative 3 times row 1 and add it to row 2. And let's do negative 2 times row 1 and add it to row 3. Okay, we got it. It's kind of tough. It looks like it'd be pretty easy, but you got to keep your eyes straight and looking at the right line at the right time. Okay, so we have x plus y minus 2z equals 3. And now here we go. Negative 3 times row 1 and add it here, and the x cancels out. Negative 3 times row 1 and add it here, we'll have negative 5y. Negative 3 times this one, we'll have positive 6z. 4z makes it 10z. And this is a common mistake. Kids always forget this, to multiply the answer side. Negative 3 times 3, we'll have negative 9. Add 1, negative 8. So our new row 2 is negative 5 plus 10z equals negative 8. Now we're doing this one. Okay, don't let your eyes wander back up to row 2. We're done with that. Okay, negative 2 times there and add it to here. Negative 2, positive 2 cancels. Negative 2, negative 3, we'll have negative 5y. Uh-oh, you see what's happening? Negative 2 times positive 2, we're at positive 4. Add it to here, to 6, plus 10z. And negative 6, positive 8 equals 2. Okay? So we're kind of seeing that these two are basically the same thing with different numbers over here. Okay, now normally in the process, you would try to get this to be a single y first, and then you would work on canceling out below. But just in the interest of jumping ahead here to see what this one is, we're going to try to cancel it out right now. Okay, so let's go negative row 2, because we're trying to cancel out that y on the bottom, plus row 3, and we'll have x plus y minus 2z equals 3 on the top. This one won't change. Negative 5y plus 10z equals negative 8. Alright, so negative of a negative makes it a positive. We add it there. Cancels. Negative of a 10, add it to 10. Cancels. Negative of a negative is a positive 8. Add 2, we get 10. So we had 0 plus 0 plus 0 equals 10. Not true. No solutions. Okay, and what we would have is that these two are parallel in a way here, and then they won't both cross this one at the same point then. So there won't be a common point to all three lines. All right, so no solutions. That's what a no solutions one looks like. Just like in with two systems. If it comes down to everything cancels out and it equals something else, no solutions. If it comes down to like 5 equals 5, infinite solutions. All right. Example 5. Solve the system. Okay. More fun. So I like that we have that 1x by itself right away, and we can use it to cancel out. And again, I'm going to cheat and do 2 steps. You're not supposed to do 2 steps at once, but we're trying to keep things efficient here. We'll go -2 times row 1, and we're going to add that to row 2. That'll cancel out that x. And then we'll do -3 times row 1 and add it to row 3, and that'll cancel out that x. So this stays x plus 2y minus 7z equals -4. Okay, -2 times row 1. So we have -2x, positive 2x, cancels. -2 times 2, we got -4y, plus 3y, we're going to have -y. We'll have positive 14z, add one more, 15z. And again, don't forget to do the constants, the answer side here. Positive 8 plus 5, we got 13. Okay, bottom row. Now again, don't let your eyes wander back to R2. -3, 3 cancels. -6 and 7 makes positive 1y. Positive 21, -36, -15z. Okay, and then we'll have positive 12 and -25, -13. Okay. Are you seeing what we have here? -y, positive y. Positive 15z, -15z. Positive 13, -13. What's going to happen when I do row 2 plus row 3? They should cancel out, right? So we're going to add those out. 0, 0, 0 equals 0. 0 plus 0 equals 0. That is true. Means we're going to have an infinite number of answers. All right, that means that those two are the same plane. 3 variables. We're talking 3 dimensions here. Okay, we're not going to be a line. We're going to have we're going to be in the plane. 3 variables here to describe the plane. Okay. And so let's see what we would do in this situation. So we're going to let z equal some a. Let z equal a. And now we're going to back substitute, and we're going to have all of our variables in terms of an a. Okay, z equals a. So let's plug that in here. Okay, -y plus 15 times a equals 13. If you add the y over and subtract the 13 over, I messed it up. 15a minus 13 would equal y. So there's y, there's z. where is our x? We're going to go back to the top. X plus 2 times 15a minus 13 instead of y, minus 7z, and z was just a. (30a minus 26 minus 7a equals negative 4. So we have 23a. Let's add this 26 over. So we have positive 22 over there. And then we'll minus the 23a. So if you want to have the a's in front or the a's second, we'll go negative 23a plus 22. So our coordinate triple, we got negative 23a plus 22, comma, 15a minus 13, and then just a for our z spot. Okay. A system of 3 linear equations in 3 variables has a similar graphical representation. It can be represented as 3 planes that intersect at 1 point, if we have exactly one solution, infinitely many points. Okay, we could intersect at a line. All 3 of them cross here at a line. Infinitely many points along that line. Okay. Or they could all make a plane, overlapping planes. Okay, they all end up being the same exact plane, also infinite solutions. They have no points in common to all 3 planes. Okay, they have common here, common here, common here, but no points are in common to all 3 planes at the same time. So no solutions there, or the 3 planes could be parallel, and then we would have no solutions either. So far, each system of linear equations you've looked at has been a square, which means the number of equations is equal to the number of variables. In a non-square system, the number of equations differs from the number of variables. A system of linear equations cannot have a unique solution unless there are at least as many equations as there are variables in the system. Okay, so if you want to get an actual answer and you have 3 variables, x, y, z, we would need 3 lines. If you don't have 3 lines, the best you're going to get is some representation like we just had up here, where 2 of them are the same. Okay, so how can I combine these? All right, same kind of ideas. We're trying to get this one by itself. So let's go with negative 2 times row 1, and we're going to add that to row 2. So we've got our x minus 2y plus z equals 2. Negative 2x, positive 2x cancels. Okay, negative 2 times negative 2, we got a positive 4, minus 1, we have a positive 3y. Negative 2 times 1, we got negative 2z, another negative z, we got negative 3z. And don't forget the answer side, negative 2 times 2, we got negative 4, and 1 equals negative 3. Okay, we want to have just y here. And luckily for us, these are all divisible by 3, so we're going to multiply row 2 by 1/3. And I'm going to bring this back down here onto the left-hand side so we'll have more room. So on the top, we got x minus 2y plus z equals 2. And then we had times 1/3, we'll have 1y minus z equals negative 1. Okay, and now we're kind of in the same situation as before. We're going to say z equals a. All right, and now we have y minus a equals negative 1, y equals positive a minus 1. And then we use our x equation, x minus 2 times whatever y is, a minus 1, plus z was just a, equals 2. And we distribute and we solve for x. I keep wanting to go with that equals, don't I? Minus 2a plus 2 plus a equals 2. So we'll have x, put these two together, minus 1a. We're going to subtract the 2 over, we get 0, add the a, x equals a. So our coordinate triple will be of the form a for the x, a minus 1 for the y, and a again for the z. Alright, we're at 26 minutes and change, assuming you did not have to pause to write anything down, so we probably are getting a little long. Let's just take a quick peek here at how you could apply this. Okay, you could use this as an application, and you could walk through the book example. You can walk through the book, their work for example 8. Okay, but here's the key here to the notes. How we can apply this. We could apply this to actually come up with a quadratic equation given 3 points. Why do we need 3 points? Because we're going to have 3 missing things, x, y, a, b, and c. So we find the quadratic equation of this form, y equals ax squared plus bx plus c, whose graph passes through 0, 0, 3, negative 3, and 6, 0. Okay? So we could come up with this by filling them in. Put 0 in here for y, and then put 0 in for x, and we'll have 0 equals 0a plus 0b plus c, or just c equals 0. Negative 3 equals, from our y coordinate, and then put our x coordinate in, we'll have 9a and 3b, and then plus c. And then for our third line, y 0 again, and 6 goes in for x, so 6 squared times a, 6 times b, plus c. Now this one was a nice one, because it did come out to c equals 0 right away, so we can use that to shorten up our work significantly. Okay, when we know that c is 0, so c is 0, c is 0. And now we're down to just a 2 by 2. Okay, we have 9a plus 3b equals negative 3, and 36a plus 6b equals 0. Alright, we're down to just using elimination, basically, like we did in the past. Let's multiply the whole top row by negative 4. We're going to cancel out our a's. We'll get negative 6b equals 12. b is negative 2. We already have c equals 0. Plug those back in and solve for a, and we get a third. So a is a third, b is negative 2, and c is 0 from earlier. Now, if you were doing this in your homework, c might not equal 0, in which case you're going to have a little bit more work and have to go through all those steps that we did in a normal solving manner. Okay, so we know them. And instead of getting a triple, this time our a, b, and c go into spots on the equation. So we're going to have 1/3 x squared. And then we'll have minus 2x, and we'll have plus 0 for the c value. And there it is. All right. Thanks for your patience, folks. Hopefully this was helpful. Best of luck, and we'll see you next time.